Hello everyone, and welcome to today's webinar, Quintus's High Pressure Heat Treatment, Combining HIP and Conventional Heat Treatment. Before we get started, I would like to go over a few items so you know how to participate in today's event. You have joined the presentation listening using your computer speaker system by default. If you would prefer to join over the telephone, just select Audio Options and leave Computer Audio and then dial in using the telephone number displayed. You will have the opportunity to submit text questions to today's presenters by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation, and we will collect these and address them during the Q&A session at the end of today's presentation.
Thank you, Clara, and thank you to everyone for joining us today. My name is Nikki, and I will be the moderator for today's webinar. Today, we will be discussing Quintus's unique high-pressure heat treatment, including advantages and real case studies. Presenting today, we will have our applications specialist, Magnus Ahlfors, presenting. Magnus, if you would like to introduce yourself and tell everyone exactly what it is you do at Quintus.
Okay, thank you, Nikki. My name is Magnus Ahlfors. I'm an application specialist for hot and cold isostatic pressing. I've been with the Quintus Technologies for 5 years now, and I am originally from Sweden, but since last year, I'm based at our US site in Columbus, Ohio.
Thank you, Magnus. If you have any questions for us throughout the webinar, please feel free to ask them in the side panel, and we will try to get back to you during the Q&A at the end of the webinar, or at least within the next day or so. I also want to inform you that you'll receive all the materials presented in this webinar, as well as the recording within 48 hours. So Magnus, why don't we go ahead and get started?
Okay, thank you, Nikki. So here's the outline of today's webinar. I will start with explaining what is high pressure heat treatment. Then I will cover equipment for high pressure heat treatment and performance, benefits, real case examples, pressure influence on heat treatment, and then I'll end up with a summary. So what is high pressure heat treatment? And here we have a poll question.
How many of you have heard or are familiar with the term high pressure heat treatment?
So here you will see you have the options of saying yes or no to this poll question, and we'll just give everyone a few seconds to get their responses in. All right, it looks like most of you have now voted, so we'll just close that and we will share the results here. There you go.
Okay, cool, interesting. Then we can move on. So what is high pressure heat treatment? Historically, HIP has been used to eliminate defects in the material only. To optimize or modify your microstructure was normally performed in other heat treatment processes. And the reason for this was that back in the day, the HIP system had a relatively slow cooling rate, so they weren't really high enough to perform many of the heat treatments. However, today we can achieve very high cooling rates in a modern HIP system. So this makes it possible to combine the HIP step with the conventional heat treatment in one cycle in the HIP. So today we can not only eliminate defects by the hipping, but we can also tailor-make our microstructure to get the desired properties of the material that we want in the HIP. So we can incorporate all kinds of heat treatment steps in the HIP today. And here are some examples. We can do stress relieving, annealing, homogenization, solutionizing, quenching, tempering, aging, etc. So if we look at this picture here, we have schematics over a conventional post-processing route. And in this case, it's towards an additive manufactured part. It can also be a casting or a MIM part, for example. So we might have a stress relief step here to reduce the residual stresses in the part. Then we have a HIP step to eliminate internal porosity. If it's an old HIP system, we would have a relatively slow cooling rate. After the HIP step, we would normally have a solutionized treatment where we have normally a very close temperature to the HIP in temperature, if not the same temperature. In this step, we normally have a high cooling rate, and then we might have an aging or tempering step afterwards. And one of the main purposes with high pressure heat treatment is to be able to combine all of these steps into one cycle in the hip. So if we see here, for example, we could in the hip do the stress relief step, then we go up and we combine the hip and solutionizing step. Then we cool fast in the hip, either to room temperature and then go up to aging, or we actually stop the quenching at any temperature and we do a direct aging. And by doing this, we have a reduced number of process steps. We can reduce the total cycle time, as we can see here, the downtime in between the processes and the lead time. We also get improved process and quality control. And from a materials point of view, it's quite interesting that we get less time at elevated temperature. If we look at the conventional way here, we might have a typical soak time in the hip process of 2 hours. And then in the solutionizing step, we would also have probably around 2 hours soak time. So in this case, we would spend 4 hours at elevated temperature. In the combined hip and heat treatment, high pressure heat treatment step, we reduce this time by half and we only have 2 hours at elevated temperature. And this can be quite important when it comes to limiting grain growth and stuff like that. So with high pressure heat treatment, we get savings in lead time. The conventional route has to be performed in at least 2 different equipment, the hip and a heat treatment furnace. If you're sourcing this service externally, this might be 2 different sites or even more different sites. So you have to ship the material back and forth to get these processes done. We also get a reduction in energy consumption. As you can see in the conventional process here, we have to heat the material up 4 times. If you combine this, we only heat up the material once. We can reduce cost and of course also capital investment because we only need 1 equipment. And here's an example of a high pressure heat treatment. So this is for a cobalt chrome material, ASTM F75. And if we look on the right here, we have a specification found in literature for the post-processing of this material. So as we can see, as a first step, we have a hip cycle specified, 1200 degrees Celsius and 4 hour soak time. And after the hip cycle, we have another homogenization step, which is performed in vacuum. This is very close temperature to the hip temperature at 1220 degrees Celsius, and also a 4 hour soak time. And then in the homogenization step, it's specified a minimum cooling rate. However, in a modern, the minimum cooling rate specified here corresponds to a minimum of 105 Fahrenheit per minute. And in a modern hip system, we can easily achieve these kind of cooling rates. So it would make very much sense to combine these steps into one. And as we can see here on the left. So in this way, we don't have to heat up the material to above 1200 degrees twice. We don't have to spend 8 hours at elevated temperature, just 4 hours. And we don't need 2 equipments to perform these 2 different steps. We can do everything in the hip. And I want to point out as well that high pressure heat treatment is not a new invention. For example, Lake City Heat Treatment in Warsaw, Indiana, they've been using this process for over 20 years by combining hip and heat treatment for the medical implant industry. For example, cobalt chrome, as we just saw. And they are processing thousands of pounds per day with high pressure heat treatment. They're operating 2 relatively large production hip units, and they're actually increasing their high pressure heat treatment capacity with a new QIH 122 on order. Looking more into detail on the equipment for high pressure heat treatment and the performance. So first, I just want to start with some history. In the 1980s, we invented and introduced a rapid cooling furnace. It was a forced convection hip furnace with the purpose to reduce the cooling time of the hip cycle so we could get increased productivity of our hip units. So if we can see here on the left, a traditional hip unit was, the cooling that you did was just to turn off the furnace and let the system cool down naturally. And the cooling time could be a significant part of the total cycle time. As we can see in this graph, we have many hours cooling where we're just waiting for the parts and the furnace to cool down so we can open the press and start a new cycle. So there's not really any value added in this part. With the uniform rapid cooling introduced, we could reduce this cooling time significantly so we can get increased throughput of parts for a given size hip. In the 2000s, we took this technology a step further, where we're looking at even higher cooling rates. And the purpose of this invention was to be able to quench materials, to actually be able to create your martensite or supersaturated condition in the hip. So it would be possible to actually do conventional heat treatments in the hip step. If we're looking closer on the technology and how we actually can achieve these high cooling rates in the hip system, if we look on the right here, we have a schematic picture of a heart of a hip unit, so which is the pressure vessel and the furnace. So we have the pressure vessel here, and the pressure vessel is water cooled. Both the cylinder and the upper and lower closure have water cooling channels. And then inside the pressure vessel, we have the furnace. And in the center of the furnace, we have the hot zone. That's where we put our parts that we're processing, and that's where we have the high temperature. As a part of the furnace surrounding the hot zone, we have a insulating thermal barrier. And this is to protect the pressure vessel from heat. So during a hip cycle, we have high pressure gas in the whole pressure vessel, but we only have the high temperature in the hot zone. So what we do when we want to achieve the cooling is we actually start to circulate the gas inside the pressure vessel. And this is driven by either a fan or a ejector or a combination of both. So what we do is that we push in cold gas from outside the furnace to inside the furnace where it cools the part, and the hot gas inside the furnace will be pushed outside, and this gas will actually be cooled down on the pressure vessel walls. And since the pressure vessel is water cooled, we can actually use it as a heat exchanger. In the case for URQ, when we want to achieve the very highest cooling rate, we actually add an additional heat exchanger into the pressure vessel. If we look at variables that will affect the cooling rate in the HIP system, we have, of course, the HIP system itself. The furnace type and the size of it will determine your cooling rate, but there's also other variables. So for a given HIP system, the cooling rate in the gas will depend on, first, the temperature interval that we're looking at for quenching. So, for example, at lower temperature, if we're hipping aluminum, for example, we have a lower delta T, and that will give us a lower cooling rate. So if we look at the right here, we have a log curve from a HIP cycle, and we can see that the cooling rate is higher here at higher temperatures than down here at the lower temperatures. The load that we're processing has also a big effect on the cooling rate. And the load on HIP language is the parts that we're treating and also the load basket. So kind of the thermal mass that the furnace have to process. So the weight of the load is quite important, how much material we're going to cool down. Also, the specific heat of the alloy that we're processing has an important factor. How much energy is stored in those parts. Also, the geometry of the parts have some influence. So that was the cooling rate in the gas. If we look at the cooling rate in the actual component itself and in the material, of course, the cooling rate in the gas will have an influence, but also the wall thickness of the component will have an influence. For example, a thicker, bulkier part would have a slower cooling rate in the center. Also, the thermal conductivity of the alloy will have an influence. How fast can we transport heat within the component? If we look on the right here again, we can see a cooling curve. So these curves are from thermocouples in the gas, and this thermocouple is measuring inside the specimen, corresponding to this picture on the top here. So I want to give you an example of actual absolute values of cooling rates in a modern HIP system. So if we take our QH48 URQ here as an example, it has a hot zone size of just above 13 inches diameter, and almost 30 inches high. The maximum load weight that we can process in this kind of hip is 550 pounds. And it's a typical size for a production machine for additive manufacturing parts. In this kind of system, we can actually achieve up to 8,000 Fahrenheit per minute, which is very fast. And I actually will give you a real case example of this here. So for this case, we have a payload of steel bars that we can see stacked like this. They weigh 156 pounds altogether. We have a single level load basket, also in steel, weighing in at 55 pounds. So we have a total load of 211 pounds of steel that we're going to process. The hip cycle for this test was just below 2000 degrees Fahrenheit and just below 22,000 psi. And we were quenching directly from the hip temperature. And here we can see the results from this test. So if we look at the temperature interval shown here, and if we look at the thermocouple in the furnace that show the slowest cooling rate, we can see that we can achieve above 8,000 Fahrenheit per minute, which is kind of impressive.
And here we have another poll question. We would like to know, did you know that these cooling rates can be achieved in a modern hip? We will give you about 30 seconds to fill in your answers, and then we will share the results with you all. About 60% of you were not aware or answered no that these kind of cooling rates could be achieved, while about 35% of you stated yes. So thank you.
Okay, cool. I'll continue here. I also want to show that a modern hip system offers a quite high degree of flexibility. It's not only high cooling rates. So we can add infinite many different heat treatment steps into the hip cycle. For example, a heating step, a soak time, cooling, quenching, etc., to really tailor make your heat treatment recipe to get the desired properties that you want. So down here we can see, this is a hardening for a tool steel. We have a typical regular heating and pumping step. We have a soak time. In the end of the soak time, we increase the temperature just a little bit before quenching down to room temperature, and then we have a 3-time tempering. Some other flexibilities in these kind of systems, we can, on the left here, we can see where we can mix between controlled cooling and rapid cooling. So in the beginning here, we have a specified cooling rate of 18 Fahrenheit per minute. And at the predefined temperature, we start the rapid cooling and cool the material down fast. In the middle here, we can see where we can actually stop the quenching. We don't need to quench down to room temperature. We can stop the quenching at any temperature, which we have done here. So we can see we have the soak time, we start the quenching, and then we stop it at 1200 degrees Fahrenheit with a slight undershoot, and then it turns into the isothermal temperature. On the right here, we can see that we also can control the temperature and pressure independently of each other. So in this case, we have a low and constant pressure in the beginning. At the same time, we're increasing the temperature. We have a hold step, increase the temperature again, and when that has reached steady state, we start to increase the pressure to typical hip pressures. So we have already discussed the benefits on the process side of high pressure heat treatment, and now we will look into more the benefits from a material perspective as well. So one thing to notice is that the high pressure in the hip remains during the quenching. So we're quenching under the high pressure. And since we have this very high pressure, we also get a very high density in the gas. And this gives us a very good thermal conductivity in the gas as well. And this in turn gives us a very high heat transfer coefficient between the gas and the components. And this is very good because then when we change the temperature in the pressure medium, the components follows closely after. If we look at more conventional heat treatment quenching processes like salt, oil, or water bath quenching, for example, where you have a hot component that you drop down into a much cooler medium, we get this initial thermal shock of the material, and this makes a risk of cracking and distortion of your parts. However, when you do quenching in the HIP, we have the components being processed and the cooling medium starting off at the same temperature, and then we start to cool the medium and the parts will follow. So it's a little bit of a softer quenching, and this gives us relatively low thermal gradients, which gives low thermal stresses that in turn reduces the risk of crack and distortion. If we look below here, we have a stress plot, and this is for a coupled FEM and CFD simulation of a URQ quench and a salt bath quench. And these were made for a hammerhead in 2 dimensions. So if we look at the simulation of the salt bath quench, we get relatively high thermal stresses in some areas of this component. And then comparing to the same kind of quenching in the URQ HIP, we can see that the thermal stresses are significantly lower. Another interesting benefit, which mostly connects to the process and quality control when doing heat treatment, is the fact that we're not moving the parts anywhere when we're processing them in high-pressure heat treatment. The heating, the hipping, the quenching is all performed in the same chamber. If we look at conventional furnaces, you normally have a furnace chamber and a quenching chamber, or you have the furnace and the salt bath. So you have to move the components between different chambers or bath. But since the component stays in the same position during the whole cycle, it's very easy to monitor the temperatures around the component and also inside the component even. So if we look on the upper right here, we have quite a large specimen in one of our smallest lab furnaces. And we can see that we have thermocouples placed in the gas all around the specimen. And in this case, we also put the specimen inside the specimen, a thermocouple inside the specimen in the center of it. So we will actually know exactly what cooling rate we have had in the center of that specimen after the cycle. We have also seen that the high pressure that we have during the quenching have some positive influence. We have seen increased hardenability for some materials and also harder martensite and final microstructure for some materials. And I will actually talk more about that later. So now I want to show you some real case examples of high pressure heat treatment. If we start with titanium aluminide, where we have done some trials with combined hipping and heat treatment. And for this material, the cooling rate very much, in the end of the heat treatment, very much decides the microstructure and thus the properties of your material. So if we look on the lower part of the slide here, these are from some trials we have made. So if you cool slow, you get an equiax microstructure. If you cool fast, you get a laminar microstructure. And if you cool with an intermediate rate, you get a duplex microstructure. And normally for this material, it's a duplex microstructure that you want to achieve to get the best creep properties. And to get exactly the desired microstructure in this case, we had to have a very good accuracy of our cooling rate to set the exact microstructure. So we had to be actually within 10 to plus minus 10 Fahrenheit per minute in cooling rate. And here's just an example how we can actually achieve that in a HIP system today, where we program 90 Fahrenheit per minute, and that's exactly what we get. Another case is for combining HIP and heat treatment for nickel-based superalloys. There's a university in Germany, Ruhr University in Bochum, that's working a lot on this topic. They have their own URQ HIP there. And this is a study that I will show a little bit about. They're looking at an alloy called Airbow 1. And they were investigating above and below gamma prime solvus temperature hipping. And they also investigated slow cooling, slow conventional cooling in the HIP and rapid quenching in the HIP. So here we can see the results from this study. If we look on the lower left here, we have the results from the below gamma prime solvus temperature. And we can see that we get quite inhomogeneous gamma prime microstructure, which is not what we desire. We cannot really see any difference between the slow cooling and the fast cooling in the HIP. When we look at the higher HIP temperatures above the gamma prime solvus temperature, we can see that we get a very nice homogeneous microstructure. However, we can see with the slow conventional cooling rate, we get quite a coarse microstructure. However, when we perform the rapid quenching in the HIP, we can get a much finer microstructure, which looks very promising for material properties. If we look into Inconel 718, which is a popular material, we have done trials for high pressure heat treatment of this as well. It's very possible to combine the conventional HIP cycle with the conventional heat treatment according to ASTM F3055 and AMS 5663. As we can see on the lower left here, this is the cycle we have done in an actual HIP here. So we have the conventional HIP cycle. We go down a little bit in temperature to the typical solutionizing temperature for this material. We cool down to room temperature, and then we heat up again to the dual step aging. And one thing to notice here is that you can make all of this process into the HIP cycle, but it's also possible to take the parts out at this point and do the aging in another furnace if that would be more beneficial. But that's very much between case to case. On the right here, we show some results for some additive manufactured 718 that was processed with different cycles. So here we can see the hardness of the as-built material, and we can see that we have some variations in hardness depending on the different builds. When we HIP the material, we can reduce this scatter in the properties between the different builds, but we get a lower high hardness. And this is for only HIPing, not heat treatment. When we combine the HIP and heat treatment in the HIP, we get a very high hardness and also very low scattering here. As we can see. We have done some trials on high pressure heat treatment of aluminum alloys as well, where we combine the conventional HIP cycle with the conventional age hardening, in this case the T6 process. And we can see the cycle here on the right. And since we're looking at lower temperatures for aluminum here, we also will have lower quenching rates. And one thing to notice here is that we will actually be have a slower cooling rate in the material compared to water quenching. And this has actually shown to give slightly less strength than the water quench material. However, when you water quench aluminum, you could have trouble with distortion and cracking, and this you will not have in a URQ HIP. So in those cases, URQ high pressure heat treatment makes very much sense. Here we're looking at a combined HIP and hardening for a tool steel. So this is pretty much the conventional process I've shown here. So we have a HIP cycle, and then we have the solutionizing cycle, and then 3-time tempering here, all according to the conventional heat treatment recipe. And an approximate total processing time of this is 17 hours. That's just cycle time, no wait time in between the different steps. And these two conventional processes were combined into one in a HIP, as we can see here. And this actual cycle took 11 hours, so we could save 6-hour time, total cycle time, saving 45%. And here we have a third poll question. Did any of these studies include the material that you are working with?
And per usual, we will give you 30 seconds to simply answer yes or no, and then we will share the poll results with you all. And it looks like almost 3/4 of you stated that yes. It's good to know that our studies do include the materials that you're working with, while about 28% of you stated no.
Okay, then we will move on here. So one distinct difference between high pressure heat treatment and conventional heat treatment is that we have the high external pressure when we do high pressure heat treatment in the hip. And this pressure in the hip can actually have some influence on your outcome of the heat treatment. So some background here, there are very few studies on the influence on pressure on thermodynamics or on heat treatment in general. There are some studies from the 1960s, 70s showing quite big effects on thermodynamics when applying an extreme high pressure on it. So these were geological studies, so they were investigating extreme pressures up to 725 KSI, for example. Stuff that they've seen is delayed phase transformation kinetics in the iron-carbon system, decrease in martensite start temperature also for the iron-carbon system, etc. As we can see here on the lower right, we have a TTT diagram, and we can see that the position of the perlite nose is very different when you perform it under atmospheric pressure or at 24,000 bar. So what we was looking to investigate was, will typical hip pressures be high enough to actually get these kind of influence on thermodynamics or on heat treatment? So we did an experiment that we did together with Sverige Akimab in Sweden, a research institute, where we were looking at how can we influence the phase transformation kinetics of a steel with hip pressure. So the approach for this study was to do kind of TTT diagram experiments. On the lower right here, we can see the schematics of the test plan. So we would heat up the material. We did an austenitization. We quenched down and stopped at the isothermal temperature corresponding to the perlite nose. And then we held this isothermal temperature for different time periods. So we got a different amount of austenite to perlite transformation. And we did these exact same thermal profiles for low pressure and a very high pressure in the hip. And then we would compare these results by microstructure analysis and hardness measurement. In this particular study, we did a steel called 4340. And here are the results from this study. So in the pictures here, this is a SEM picture, and you can see that the dark fields are perlite and the brighter fields are martensite. And if we look at 1500 seconds of isothermal time and at the low pressure, which were 10 megapascals, for that case, we got 19% perlite. For the exact same thermal profile, but at 170 megapascals, so the much higher pressure, we only got 10% perlite. So we could see a difference there. When we moved further into the transformation at 2000 seconds of isothermal temperature, we could see that when we processed with the low pressure, we got 70% perlite. And when we processed the same thermal cycle with the high pressure, we only got 26% perlite. So quite a big difference there. And looking at the hardness as well, it shows the same results, 344 Vickers versus 497 Vickers. So the conclusion from this study was that we can actually affect the phase transformation kinetics for a steel with hip pressures. And what it means is that we actually get increased hardenability when we're quenching in the hip. And this makes it possible to either use less alloying elements in your material and you get the same quenching response. You can quench thicker sections and get the same hardening response, or you can just cool slower to get the same hardening response. And the theory of this reduction of transformation is that the high pressure stabilizes austenite, so it suppresses the austenite to perlite transformation. There's also a contribution for lower carbon diffusivity when we have elevated pressures. Another study that we made together with Sverige Akimab in Sweden is to perform the full age hardening cycle of 74 pH in the hip and compare with the same material but processed in the conventional way, so in a vacuum furnace and water quenching, and then compare the results. So what we saw in this study, what was quite interesting, is that the material processed in the conventional way with vacuum furnace and water quenching got a certain type of hardness in the quench state and in the final age hardened state. However, the same process performed in the hip under pressure actually gave higher hardness both in the as quench condition and in the final condition. So this means that you would automatically get a material with higher hardness when you're performing the age hardening in the hip for 17.4 pH. And the theory here of why we have this higher hardness in the martensite or in the final microstructure when we do it under pressure is that the high pressure promotes the more closed pack crystalline structure, and the martensite is less close packed than austenite, so this will push the martensite start temperature to lower temperatures, and when you form martensite at a lower temperature, it will be harder. So some general conclusions from pressure influence on heat treatment. So when we look in the literature for CCT diagrams, TTT diagrams, heat treatment recipes, or thermodynamics in general, everything is for atmospheric pressure. There's very limited data on the pressure influence on thermodynamics on heat treatment. So in these two studies that I showed you, it was just concerning the steel, and just two different effects were investigated. So there's a lot out there to be investigated. It's a very interesting and unexplored field where research is needed. And we won't be able to cover all that research, so I hope that some of you out there will be able to help us with that. Okay, so that was my talk for today. I will summarize with as we started with, high pressure heat treatment. That is when we're combining hip and conventional heat treatment in one cycle in the hip. The main purpose of it is to reduce and eliminate process step. A modern hip system, we can achieve very high cooling rates up to 8,000 Fahrenheit per minute. And we also have a very high degree of flexibility to tailor make our high pressure heat treatment recipes for the desired properties. Some more process benefits of high pressure heat treatment: we get reduced cycle time, lead time, energy consumption, capital investment, cost, etc. And we have excellent process and quality control. As I just mentioned, high pressure can influence the outcome of the heat treatment. It's a very interesting and unexplored field. So this was the second part of the webinar covering high pressure heat treatment. For the next part of this webinar, the final part, we will look at hip and high pressure heat treatment for additive manufacturing materials specifically. So what are the specific requirements and aspects when hipping AM parts? That webinar will be launched on March 20th on 11 a.m. EDT, and a separate invitation will come for that. The outline for that webinar will be challenges within additive manufacturing, special requirements and aspects when hipping for AM material, benefits of hip and high pressure heat treatment for AM material, and real case studies of AM materials being hipped and high pressure heat treated. I also want to mention again that we will all be at Rapid, the Quintus team, in May in Texas. We have booth 509, and you're very welcome to come up there and ask us any type of questions about hipping in general, or any other type of questions. So that was it for me. Yeah.
So now we're going to begin answering the questions that were submitted during today's presentation. As a reminder, you can still submit questions through the questions pane in your attendees control panel. So our first question today will be from Dave. And Dave asks, what is the biggest size systems where your high pressure heat treatment process can be applied.
Okay, and I would say there's no real size limitation on high pressure heat. It will very much depend on what cooling rate you need for the material, because the very biggest HIP systems, they don't have 8,000 Fahrenheit per minute. They will have slower cooling rates, but I mean, as I mentioned, Lake City Heat Treatment, they're doing high pressure heat treatment for cobalt chrome, and they're operating, big production HIP systems, and they can achieve the cooling rate needed for that material. So it depends on the cooling rate you can achieve in your system and the cooling rate you actually need to process the material in the way you want.
Okay, thank you. The next question is from Sania. What is the need for stress relief? Because HIP can stress relief as it's done at higher temperatures than stress relief step.
I will read this again. Yeah, regarding stress relief, if we look at additive manufacturing, you can do that in the HIP on the build plate before you remove the part from the build plate. You can also do it before you actually start your HIP cycle. The temperatures for the stress relief itself, I would just copy whatever conventional stress relief we're doing outside the HIP to make it inside the HIP. But there's a difference to actually HIP the parts on the build plates or to stress relief, remove them from the build plate and then HIP them. It will depend on fill grade and stuff like that.
Okay, and the next question is from Julio. How is the controlled cooling steered in the modern URQ HIP unit?
Okay, so when it comes to controlled cooling, there's some different aspects of it. It depends kind of on the furnace design, what size of furnace it is, and what kind of cooling rates you're looking at. So between 0 and 30 degrees Celsius, now I'm in Celsius, per minute, you can control exactly what cooling rate you have, and that you do with by adjusting the heat furnace power into it. When it comes to higher cooling rates, we have one type of furnace that using an ejector, and in that way it's not completely controlled cooling. We can't program an exact cooling rate like 7,500 degrees Fahrenheit per minute. But we could, there is different things you can do to change your cooling rate, but it's not fully programmable. If we look at bigger systems with URC or URQ, where we actually use a fan, then we actually have thermocouple feedback control of the RPM of the fan, so we can actually program an exact cooling rate, and that's what we will give. So it depends a little bit on the furnace design and the size of the HIP, etc.
Okay, and the next question is from Sarah. On the 718 HIP/heat treatment HV graph, were the samples fabricated in a laser or electron beam system?
It was a laser system produced at University West in Sweden.
Okay, thank you. Our next question is from Johannes. Why do you slightly increase the temperature before quenching?
Yeah, that's a good question. I mean, you can't. I showed that it's possible to do it. You can also decrease your temp. In that case, it was that we wanted to HIP the material. We wanted to minimize grain growth, so we HIPed at what we considered a minimum HIP temperature. But then we wanted to go up to the conventional solutionizing temperature before quenching. So that was quite the reason. But that's very much specific from case to case. We saw in the graph of Inconel 718, we actually have a higher HIP temperature than the conventional solutionizing temperature. So in that case, we actually went down in temperature before quenching.
Okay, and another question we have is from Sudip. Was any study done on high gamma prime alloys under pressure?
Might be. The studies that we showed here for Inconel 718 and the Airbow 1, that's the studies we have done mostly. And I don't think we have too much material on high gamma prime alloys.
Okay. Another question is from Andy. We are interested in evaluating high pressure heat treatment at some of our materials. Are there any service providers that can offer this today, or can you help us with this?
Yeah, so we have Quintus Technology. We have a lab in the US, in Columbus, Ohio, and we also have a HIP lab in Västerås, Sweden, where we're based. So that's pretty much what we do with our HIP labs. We're evaluating new types of HIP cycle, high pressure heat treatment cycles, etc. And we don't do too much research of our own. We normally work with partners, collaborations. So if any of you out there is interested in trying high pressure heat treatment on your material, on your specification, you're very welcome to contact us, and we can do a test program together.
Another question is from Tracy. She asks, the cooling rates are really impressive. For what materials do you see this being mostly beneficial?
Okay, so most beneficial. I mean, different kinds of materials will give you need different types of cooling rates to get the desired microstructure. And the very high cooling rates will probably be most needed for aluminum alloys when you do age hardening of aluminum, also martensite tempering of steels, those kind of materials. But then, of course, we saw that cobalt chrome needs minimum 60 degrees or 105 degrees Fahrenheit per minute to avoid carbide formation. And I mean, that's not a very big, a very high cooling rate.
Thank you. Another question is from Lene. Are there any specifications for the high pressure heat treatment cycles?
Specifications? No, there's no standards for it. What we do when we do high pressure heat treatment, it's pretty straightforward. We know what the conventional HIP cycle for the material is, and we probably know what the conventional heat treatment recipe for that alloy is, depending on what we want to achieve with our material. And I mean, it's easily found in literature. So it's pretty straightforward. We just combine the HIP cycle with the heat treatment recipe in the HIP, and we get both the hipping, both the defect elimination and the microstructure optimization of the material in the same cycle. That's pretty much how we do it. So there's no specific specification for high pressure heat treatment yet. I would say it might come.
And our final question today is from Pablo. Would you recommend a solution treatment before the HIP process in the case of a precipitation hardened steel? And what hipping conditions would you recommend in these types of steel?
Okay, so I would not recommend, if you're doing hipping and heat treatment separately, you would do first hipping to close your porosity, and then you would do the heat treatment to set your microstructure. If you do a solution heat treatment, let's see here, if you do a precipitation hardening before the HIP cycle, and you get your desired microstructure, when you HIP it, you will destroy that microstructure again. So I would not recommend that. So either you do it separate processes because you can't cool, you can cool fast enough in the HIP, or you combine the two together. And what hipping condition would be recommended for this type of steel? Well, I'm in SI units, but pretty much all steels are hipped at 1150 degrees Celsius, minimum 100 megapascals, and 2-hour hold time, depending on size of components. Yeah.
Okay. Well, thanks for that. Thank you, Magnus. And from Quintus, we would like to thank you to all of you that have attended today's webinar. You will also receive a follow-up email within 48 hours with a link to view a recording of today's webinar. And again, we would just like to thank you for joining us today, and we hope you have a fantastic rest of your day.